There he started his education, and now he has his Doctor of Philosophy degree in Chemical Engineering from Case, member of today's Case Western Reserve University. After successful years in the teaching profession at universities in Cleveland, he worked as an aeronautical research scientist at NASA and became one of the first 40 rocket scientists at NASA's Cleveland laboratory. In 1956, Dr. Ladanyi founded his own company and works on rocketry-related problems even today. Here is Dr. Ladanyi.
I don't know if I should use the microphone or not. Can you hear me without a microphone? Is this better? Which one would you prefer? Microphone? Yes. I was prepared to come here tonight and fill you full of all sorts of lies and exaggerations, but I see that one of my contemporaries from NASA is sitting right here, and so I have to stick to the truth now. That's Riley O. Miller. He preceded me in the rocket field. He was one of the really early rocket scientists in this whole darn country. And he did some very, very basic work. About a year ago, I was requested to prepare a lecture for this program on entrepreneurial Hungarian Americans in the United States, and especially in Cleveland. When I discovered that this would be an enormous task, I received permission to narrow the subject down to the field of rocketry. And with my background in this field, the job became quite a bit easier. My first 4 years with the National Advisory Committee on Aeronautics, which is now called NASA, was spent in doing research in bearing technology. About 1948, I was assigned to a new section dealing with rockets. There were only a few of us at that time, and we were on the bottom of the totem pole when it came to receiving funds for research and development. Right, Riley? We were relegated to some dingy old buildings on the edge of the NASA property where the bigwigs hoped that we wouldn't bother them. And we didn't, except for a few explosions now and then. Nobody knew that we even existed. When friends would ask me, "What kind of work do you do?" I'd say, "Rockets." And then they would laugh and make ridiculous remarks saying, "Bang, bang, bang," you know, and make a lot of fun out of it. So after a while, I learned to say when they would ask the same question, "I am an aeronautical research scientist," and the answer apparently satisfied most people. In 1948, it is true that the general public would think of fireworks when the word rockets would be mentioned. It may be of interest to you to know that rockets were used by the Chinese as early as the 13th century. Interest in rocket projectiles was not aroused until the beginning of the 1800s, when the successful use of solid propellant rockets by the British indicated that these new weapons might eventually replace all land artillery. The later rapid improvement of the accuracy of guns and mortars made the relatively inaccurate war rocket obsolete towards the end of the same century. The next big step in rocketry was the invention of the liquid propellant rocket. A Peruvian by the name of P.E. Paulette claimed the first practical working model in 1895. The propellants were not self-igniting, and a spark ignition had to be used. In 1923, Professor Hermann Oberth of Germany published a detailed mathematical theory for rocket projectiles. A notable achievement in the development of liquid rocket propellants was the German V2, and I'm sure most of you older people remember that. It was a supersonic ground-to-ground missile with a maximum range of about 250 miles. Its fuel was water-diluted ethyl alcohol, which is similar to what you drink at a bar, and its oxidizer was liquid oxygen. Next time you have your favorite drink, make sure that you don't wash it down with liquid oxygen, otherwise you'll take off like a rocket. In this country, the United States, Professor R.H. Goddard is called the father of American rocketry. In 1919, he described a method for reaching high altitudes with a rocket. Other rocket enthusiasts formed the American Rocket Society in 1932. You remember, weren't you, Riley? What year did we join it, do you remember?
What year did we get it?
Yeah. It was early 40s, wasn't it? Anyway, some of the prominent members of the society formed a company called Reaction Motors, which made successful rockets during World War II and developed a rocket propulsion system used on the XS-1 supersonic plane, which flew faster than 1,000 miles an hour. And keep in mind that this was done more than 30 years ago. So we have pretty fast flying planes even at that time. Another important group formed in 1940 as the Jet Propulsion Laboratory of the California Institute of Technology. They developed a self-igniting liquid propellant combination and first used it successfully in 1942. More about this group later. Up to this point, we have been talking about rockets, and perhaps a number of you don't really know what a rocket is, nor how it works. Or maybe you don't care. However, this might be a good time to look into the matter of what a rocket is. I'm now going to make a real rocket engine in front of your eyes, and then I'm going to launch it for a first flight. And my assistant, who happens to be my younger son, Albert, will help me in this. Okay, Albert, start making a rocket. First, he has to make a chamber, and here he goes. Okay. Now, this blown-up balloon is indeed an actual rocket engine. In flight, it will demonstrate Newton's third law, which states for every action there is an equal and opposite reaction. Right, John? Okay, I see you nodding, so either you're falling asleep or you're agreeing with me. All rockets follow this law. This rocket has all the components necessary to make it work. It has an outside covering which covers a gas. Show them the outside covering. And the gas in this case is air. And it's under pressure. And it came from a big blowhard who blew it up. And it's hot air too. It has a nozzle at one end. Show them the nozzle. There's the nozzle. And through this nozzle, the pressurized gas will leave and propel a rocket. Now, it's not moving now because the nozzle is closed and none of the gases are leaving. As soon as my son lets go of the end, the nozzle will open up and the rocket will take off. He's going to demonstrate. There was a rocket. You want to try a bigger one just in case? No, the other one, the red one. All right, go to it. The reason it wiggles this way and that way is it does not have stabilizing fins and wings and other things to make it go right. See, there you go. And that's exactly how the first American rockets went, believe it or not. This simple rocket did not go far because the propellant, which happened to be the pressurized gas, was quickly exhausted. If we could find a way of replenishing the supply of propellant in flight, this rocket would go on indefinitely. Unfortunately, as I said before, this rocket did not have stabilizing fins as a guidance control, and therefore its flight was somewhat erratic. Okay, now I'm going to get a little audience participation here. And I see a whole bunch of engineers, so you fellows know the answer, keep quiet. But I'd like to ask some of the laymen here this question. How did the rocket work? What made it go? Okay, volunteers. Where's Dorothy? Dorothy Boland. What made the rocket go?
Hot air. Albert's hot air.
That's not an answer as to why it went.
Heat.
What?
Heat.
Heat for?
Heat from one source to another.
No, heat had nothing to do with it. If he blew cold air in there, it would have done the same thing. Well, okay, so the air did come out, right? Under a small hole, but why should the rocket go? Why didn't the air just come out and the rocket sit there? Why should the rocket move?
Force.
Yes?
Move faster out of the smaller opening. My sister said pressure.
Well, I gave the answer before, but maybe you didn't listen carefully. I said for every action, there's an equal and opposite reaction. And this is Newton's third law. What is the action? What's the reaction? Maybe I'll ask my granddaughters here. Shelley, what's the answer? Here comes Ted Bolett. Let's see if he knows the answer. He is one of the outstanding Hungarian-American engineers in this country. And while you're undressing, we just gave a demonstration of a rocket in the form of a balloon, Ted.
Yes.
What made it run? What made it work? I asked the other engineers in the audience not to reply because I wanted to see what the lay people would do. I want to see what an engineer will say.
It's the reaction of the escaping gas pushing on the balloon.
Well, most people will say this, and is this not true? As the gas goes out, it pushes against the air, right? And when it pushes against the air, then it moves. Like when you go in a rowboat, you push against the water and it moves, correct? Right? Mm-hmm. Everybody agree?
What if you're in a vacuum and there's no air to push against?
What if there's then it won't work, will it?
But it does.
But it does. You're too smart, Ted. No, that is not the reason. Most people, a long time ago, and even today, believe that this is what really happens in a rocket. The gases come out and push against the air, and it goes in the opposite direction. That's not true. Let me show you a point here. Here's a wall. Okay, now I'm going to push against the wall. I'm going to push pretty hard. And Newton's third law is now working. I'm pushing, let's say, with a force of 100 pounds. The wall pushes back equally with a force of 100 pounds. Is that true or not? The wall is pushing back at me. Now, think a little bit and you could see the answer immediately. If the wall did not push back with a force of 100 pounds, let's say push back with only 80 pounds, what would happen? The wall would fall over. If it pushed with a force of more than 100 pounds, then the wall would come out at me. So it has to be exactly 100 pounds. Okay. It was way back in 1912 that Dr. Goddard, at one time everybody thought the world was flat, and somebody had to disprove it. So he had to disprove the idea that Goddard had to disprove the idea that the escaping gases were pushing against air. So he made a little rocket, solid fuel rocket. He tied it down real tight, and he put in a tank with glass around it. And he evacuated the tank. There was no air in it whatsoever. He started up the rocket, and it ran like a charm. Okay, let me show you exactly why a rocket works. And from now on, after you leave this auditorium, you'll know more about rockets, including myself and Riley over here. Let's make another rocket, but this time we'll make it pictorially. And Albert, would you help? Over here. I'll start here. But I'll be using that right now. I'll take a Coca-Cola thing. Now, this is better than a balloon because instead of having an odd shape, it's got a rather nice cylindrical shape. And this is the front of the rocket, and this is the rear end. Now, if I fill this rocket somehow with high pressure gas, and if I held my finger on the back of it, nothing would happen. All I would have is a can of high pressure gas. As soon as I let go of there's a hole in the back. As soon as I let go of that hole, the can will take off and go like the balloon did. We'll start with figure 1, which shows a very, okay, turn this off. Can of any sort. And this one is a metallic can, let's say. Then we put a hole in one end, similar to this empty can that I have here. Albert, put a hole in the end of that can. Figure. This time I put a hole in the end of it. Somehow, if we put pressurized gas in it and seal the end off, with my fingers, I said before, and if I'm strong enough, and I let go of the end, the can will take off just like a balloon did. Now, with my fingers, or with my finger on the hole, the molecules of the high pressure gas are pushing equally in all directions. If I have my finger here, the pressure is the same on the top of the can, the bottom of the can, and the sides of the can. So there is no difference in pressure no matter which way you look. In all directions it's the same. For any point on the can, for any point on the top of the can, for example, there's another point directly opposite on the bottom. And the force is equal on both of these points, except they're in opposite directions. Therefore, the can does not move. And this is true for every pair of points on the inside of that can. When I uncover that hole, the total force against the hole in the bottom of the can, over here, is what? There is no force because the gas comes pouring out, so the force against that hole is essentially zero. But directly opposite, on the top of the can, there is an area which is the same size as the hole, and in other words, if you peeked in the bottom of this can, you would see an area directly opposite on the top of the can, and it's the same size. Since the can is intact, the pressure against this area is about equal to the pressure everywhere else on the inside of the can, except at the location of the hole. If the area of the hole is, for example, 1 square inch, and the pressure in the can is 50 pounds per square inch, a little bit higher than you have your automobile tire, for example, there will be a force of 50 pounds pushing against the top of the can with no opposing forces on the bottom at the hole area. Therefore, the can will move in the direction of the top. In this particular case, we say that we have a rocket with a force of 50 pounds, and in rocketry, we would have called it a thrust of 50 pounds, if I remember right, Riley? So, in this particular picture, I have shown on the top, inside, that is one area where the gases are pushing, and there's nothing to balance it. So it will go in that direction. The balloon did that, and the can will do exactly the same thing. With the hole here, the can would go in that direction. Now with the molecules of the gas rushing pell-mell out of the hole, there's a lot of turbulence which causes inefficiency because the molecules bump each other and they say, excuse me, and what are you're my way and everything else, and that's not good. Therefore, we add a converging nozzle as shown in the next figure. There we have the same can, but I put a little nozzle on the end of it. By converging, that means to go from a larger area to a smaller area. Now this helps, but the convergence of the nozzle makes the molecules run into each other. So now we extend the nozzle with a diverging system as shown in the following figure. Okay, now this is what we call a converging, diverging nozzle. It goes first to a smaller point and then it opens up. And the smallest point has a special name. Does anybody know what that name is called? In that nozzle? That's the throat. That's the throat of the nozzle. Perhaps you have seen such nozzles hanging down from the rockets, which are shot off at Cape Canaveral. My older son Don just came back from Cape Canaveral. He was waiting to watch the launch of the latest shuttle flight. So he went up in an airplane and he was circling the area. And he took some pictures, but you have to have a video TV screen, and we don't have one here now, but it would be real interesting to look at. In this case, as with the balloon, the gases are used up quickly. Therefore, we have to replenish the supply continuously. And we do this by drilling holes in the top of the can. Let's drill a couple of holes, Albert. And we screw in a couple of injectors, which are plugs, ordinary plugs with a small hole in each one. These are the two injectors which we put into the top of the can. We feed fuel through one injector, namely on the left-hand side, and we feed oxidant or oxidizer of some sort through the other one. The fuel and the oxidant or oxidizer, you can use either name, are called propellants. The fuel won't burn without the oxidant. For example, one familiar oxidant used in rocket work is liquid oxygen. So you always need both. You can't have one without the other. You know, like in a tango, you can't tango without two people. The injectors are aimed so that the propellant streams hit each other and mix well. And depending on the propellant combination, the propellants will ignite by themselves, or if necessary, by the use of some form of energy, such as a spark plug in an automobile engine. The fuel will come in here, will hit, and then it'll swirl around and ignite, build up gases, and as long as you keep on pumping fuel and oxidant, the rocket will go. The burning propellants will quickly build up pressure in the can, and this can, by the way, in rocketry has a special name. What do we call it? We call it the combustion chamber. Okay. And it expands very rapidly. The rocket will then move as the exhaust gases go out of the nozzle. And as long as you keep feeding the propellants to the combustion chamber by pumping them out of their respective storage tanks, the rocket will continue to operate. Of course, the whole package moves. And that includes the storage tanks, the pumps, the connecting lines, and everything. Everything moves. And if they didn't, you'd have a problem. Now, these components are usually bundled together rather neatly, and not as shown here in my particular figure. About 30 years ago, General Electric was having trouble igniting their rockets. One of the first, I think that's the last one, Albert, on that batch. Thanks. One of the earliest rockets in this country was produced by General Electric. It was called the Vanguard rocket, and they had a lot of trouble with it. maybe you remember seeing pictures of them. They were great big long things and skinny, and they would put them up on a launch pad, and then they would ignite it or try to ignite it, and the flames would burn, and either you'd hear a big bang, the thing would blow up, or if it took off, it'd wobble a little bit and then fall over on the side. But you gotta have failures before you have any successes. We invented an igniter to work on the Vanguard, and the igniter was nothing more than a miniature rocket engine. And I have one here in my hand. Now I have the complete setup, which is portable. I was going to bring it here tonight, and my son and I worked on it last night, and we decided not to try it in this auditorium because I would have lost my audience rather quickly. The noise is pretty darn loud, and everybody would have run out of here. But let me show you what a miniature rocket engine looks like.
Here's the combustion chamber, this little part here. This is the nozzle on the end. These are two lines going in. One is a fuel line, the other one is an oxygen line. This particular engine could not ignite by itself, so it had to have some external force of energy, which in this case happened to be a spark plug. I then took this little rocket engine and we screwed it into a big rocket engine that they were using in the Vanguard system. So what we did was to push a button. This spark plug would ignite the gases going in there, and the gases were nothing more than gaseous oxygen and propane. And then we'd get a big flame out the end. And that in turn would ignite the big rocket engine. You can look at this later if you want to.
Now that you know how a rocket engine operates, let's continue the lecture. Do you all know how it works? Fuel, oxygen, you put it through a head of some sort, injector head we call it, through injector nozzles. They go into the combustion chamber, they mix, and then they ignite, and they build up pressure, and the exhaust gases go out the rear, pushing the nozzle forward. I mean, pushing the rocket forward, as you now saw by our demonstrations. How many of you knew that's how rocket engines worked?
What's the purpose of a rocket? Am I going to be hot?
Yeah, you missed the first part of the lecture when I described that part.
Why do they make rockets?
Well, we'll get into that. And there are two types of, this rocket engine we just discussed falls into the category known as jet propulsion. There are two types of jet propulsion. One in which the matter to be ejected out the rear is contained wholly within the device, inside of it. And the other one is one in which the matter to be ejected is obtained from the surrounding fluid, whatever surrounds the device. And the fluid could be either a gas or a liquid. And this is then ducted through the device and accelerated to a greater momentum by mechanical or thermal means, by heating it up or doing something with it prior to ejection. The first one I just described is called rocket propulsion, and the latter one is duct propulsion. Whereas a rocket in operation is essentially completely independent of the environment, since it carries both the fuel and the oxidizer. A ducted system, such as the jet engines in an airplane, carry only fuel, and they must depend on their surroundings to get the oxidizer, which is usually air. For that reason, a jet engine or your big airplanes, they can't go up and up indefinitely because they won't get enough air. And then they'll fall down. Okay, enough of rockets for a moment, because remember we're here to talk about Hungarian Americans in rocketry. By now you may ask, where do Hungarian Americans come into the picture? Perhaps the greatest one of all in the entire rocket field was a gentleman by the name of Theodore von Karman, I would say. His contributions were so great, and you have heard so little about him. Maybe it's because he was Hungarian, I don't know, but we should take a little time to look at his background in detail. And this is one of the factors that the doctors Ilona had asked me to cover. He was born in Budapest in 1881. He was the son of Maurice Karman, a university professor of education who was knighted in 1907 by Ferenc József of Austria-Hungary for reorganizing Hungarian secondary education. And his mother was Helen Kohn, the descendant of a distinguished Bohemian Jewish family. As a young man, Karman won the Eötvös Prize. Ted Bola gave a big speech on Eötvös at one time, but he won the Eötvös Prize for science and mathematics before entering the Technical University of Budapest. Later, he did postgraduate work in Göttingen, Germany, in the field of aerodynamics, working under the great father of aerodynamics, Ludwig Prandtl, which doesn't mean much to any of you except those of you who are engineers. Before leaving Göttingen, Karman developed an answer to a phenomenon which later became known as the Karman vortices. I'll skip over that. If you're interested later, I'll describe what this was. But the failure of the first suspension bridge at Puget Sound up in the state of Washington was shown by Karman to have been caused by these Karman vortices, which were created when a wind reached a velocity of only 42 miles per hour. Remember that bridge that swung back and forth, and finally fell into the water? After teaching, there's so much on Karman that I had to condense a tremendous amount of material into a short amount of space here, so excuse me if I leave out some of his important things. But after he taught school in a mining college in Slovakia, Karman secured a professorship in Aachen, Germany, where he remained until 1929. There he became heavily involved in the development of aviation. And believe it or not, this Hungarian laid the foundation of a new German Air Force, which became popularly known as the Luftwaffe of World War II. During 1926 to 27, Karman made an extensive trip to the United States and to Japan. And in the United States, he spent some time at the California Institute of Technology in Pasadena, where a new aeronautics laboratory had been endowed by Daniel Guggenheim. Soon after his return to Aachen, Karman received an offer to become director of the Guggenheim Aeronautical Laboratory from Caltech's famous chief, R.A. Millikan, and I'm sure you've heard of his name. He accepted and left Aachen at the end of 1929, and he stayed at Caltech for an enormously long time. And his long tenure at Caltech saw its emergence as one of the top aeronautical research centers in the entire world. But perhaps even more important were his contributions to the teaching of aeronautical engineering, which he put on a scientific, especially a mathematical basis. A substantial number of professorial chairs in aeronautics in the United States and other countries came to be occupied by Karman's students. One of his students from Shanghai ultimately returned to China, where he contributed substantially to that nation's technological development. Another one of his students rose to great fame as an airplane designer, and he was the one who designed the DC-6. Karman's presence at Caltech also played a part in the development of the aircraft and space industry in Southern California. He helped to found the Aerojet Engineering Corporation, which later grew into one of the industrial giants of the jet age known as Aerojet General. And I'm sure you all have heard of that company. Another development deriving from Kármán's activities was the organization of the Institute's Jet Propulsion Laboratory, known as JPL by everyone. And it's a government-funded center of rocket research and space communications techniques that is acknowledged as a principal contributor to America's preeminence in space technology. Originally concerned primarily with rocket research arising from military requirements during and after World War II, the laboratory was greatly expanded after the United States entered the field of space exploration and shifted its emphasis to propellants and to remote control. But the aerodynamics research started by Kármán remained a concern of the laboratory throughout all this time. Kármán was a valued consultant of the United States Air Force, and he played a part in its emergence from a subsidiary position as a branch of the United States Army, and I happen to be in the United States Army Air Force. It rose to an autonomous stature. He was a chairman of a committee that produced a famous report called Toward New Horizons, which became the blueprint for the new Air Force. He subsequently served on the Air Force's Scientific Advisory Board. He also helped to organize the RAND Corporation, that real famous think tank similar to Battelle and other companies. When NATO, NATO was organized in 1949, Kármán proposed the organization of the Advisory Group for Aeronautical Research and Development. And you probably know it by its initials, AGARD, A-G-A-R-D. It used to be in the newspapers quite often. Under his leadership, the International Aerodynamics School, known as the Training Center for Experimental Aeronautics, was established. Because of his contribution, later its name was changed to the Von Kármán Center. He also played an important part in the formation of the Advanced Research Projects Agency of the United States Department of Defense. Kármán received many honorary degrees and medals, including the United States Medal for Merit in 1946, the Franklin Gold Medal in 1948, and the National Medal of Science from President Kennedy himself in 1963, as well as most awards given in aeronautics and fluid mechanics. He was also commander of the French Legion of Honor. He was a member of the Pontifical Academy of Science, and he was also the recipient of similar decorations from Germany, Greece, Spain, and the Netherlands. He was the author or co-author of 171 papers and articles, and he also wrote 5 books. In his late 70s, Kármán started his autobiography. The work was about 3/4 finished when he died, but the Air Force, United States Air Force, thought so much of it that they underwrote its completion from the remaining tapes and interviews. And it was ultimately published with the following title: The Wind and Beyond, Theodore von Kármán, Pioneer in Aviation and a Pathfinder in Space. My wife wanted me to bring a copy of this book down, but we didn't have a chance to pick it up from the library. You can pick up the name later if you're interested. Kármán never married, and he died in Aachen, Germany in 1963. Despite his many public activities, he never became a great public figure in the way of many inventors, perhaps because theoretical aerodynamics is not a very accessible field to the layman. In other words, it's over most people's heads. Nevertheless, his work in that field and in rocket research has helped shape both scientific and political history. Now, how's that for a prominent Hungarian? I think he's pretty good. I have a list of 22 other engineering-oriented, entrepreneurial Americans of Hungarian descent with me today, and I include myself among them. But I am tempted to say that all of us put together cannot match the worldwide contributions made by Karma. He was really great. Okay, let us look at some other events in the progress of American rocketry, especially those with I am personally familiar. Maybe I can take a little rest now. Are there any questions from the audience? I saw some hands going up periodically, and you wanted to ask me something, and if I can't answer it, my colleague Riley Miller here will. Yes?
Nothing, you haven't said anything about solid propellants.
No, not yet. There are two types of rockets, two main types. One is one which has solid propellants. That can that I showed you, I could have filled that with a solid propellant, okay? And then put a match to it or something, and then let it burn. But what's bad about a rocket propellant? Why aren't they using it very much nowadays? Okay, I'll ask you, what's wrong with a solid rocket propellant?
I don't know, it's a little, I don't know how to express it in engineering terms.
No, you don't need engineering terms.
It's not as efficient as...
Oh yes, it's pretty darn efficient.
Then it is efficient, but it's too much weight or mass.
No.
And I don't
There's
know-
only one answer, one answer only. Yeah, you can't turn it off. Once you light it, it's going to go, and you say, hey, I'm at the end of the trip. The rocket says, no, I got some fuel left. I'm going to keep on going. And what are you going to do, put your hand on the end? You can't. No, that's the biggest detraction from a solid propellant rocket. Okay, you wanted to ask something a couple of times?
Scratching my head.
Pardon me?
Just scratching my head.
Oh, well, that's a question too. Ted?
The minor disadvantage, the solid propellant doesn't always burn evenly. You got a lot of wobble in there. You get much better.
Okay, now he brought up a point which I wasn't going to bring up, but as the solid propellant burns, and you know burning takes place only on a surface, right? What's happening to that surface inside the thing? It's getting larger and larger and larger and larger. So how can you make a rocket go evenly if your burning is uneven like this, right? Right, there's a way of doing it. And that is, when I left NASA, they had some solid propellants in which the surface of the solid propellant was cut in such a manner that as it burned, believe it or not, the surface area remained constant. And that's a pretty good trick. Today they would do it with computers, I suppose. Remember that, Riley, how that worked? It looked like, you know, when you take an apple, you cut a bunch of teeth in it, you pull it apart and you can put it together. No? Okay. Any other questions?
How do you spell Mount Carmel?
Pardon me?
How do you spell Mount Carmel?
V-O-N. You want the rest? K-A-R-M-A-N with two lines on the two A's. Karman. Well, okay, I'll continue. Back in the late 1940s, there occurred a behind-the-scenes national controversy, and most of you have never heard of it. So here's where I throw the papers away because I was intimately involved, and so was Riley Miller, and so were all the other boys at NASA. Here's what happened. For 2 years previous to that, Riley and I and some others had been working on a phenomenon in liquid rocket propellants known as ignition delay. Now what does that mean? When you inject a fuel and an oxidant into a rocket, they come in, they hit, they don't ignite right away. It takes a little time. And I'm talking about self-igniting rocket propellants now, not those that need an outside energy like a spark plug. The two jets come together and they mush around inside of the rocket chamber until finally ignition takes place. Well, why doesn't it happen instantaneously? Because when they fuel and oxidant go in, they're relatively cool, room temperature, they hit, the chemical reaction starts, it gets hot. The higher the temperature, the faster the chemical reaction. And then one thing leads to another, they get all excited, and the molecules start jumping around and going crazy. And finally they say, we can't take it, and then it lights up. That's ignition. The catch is that ignition has to take place pretty quickly, or you're going to have a lot of trouble. And this is exactly what happened. Riley was the first one, I think, to work on a system whereby he took little balls of, if I remember right, propellants. One is the oxidant, and the other one was the fuel. And he put them into a tube, and he smashed them together, and then he timed the length of time it took to produce ignition, or a rapid reaction. And if you want to know more about it, he's here tonight, so you can ask him later. How's that for pushing on you? Well, what happened was that in the late 1940s, the Navy, the Department of Navy, said the only way to fight a war is to use fast-moving fighter planes. And with a fighter plane, we can go and we could, we see a bomber and we'll just go right in and we'll shoot the bomber down. And the Army says, the Army, on the other hand, was in favor of producing a lot of bombers. Now with a bomber can fly real high. And although it's much slower moving than a fighter plane, the Army felt they were invulnerable because at that time, if a jet engine wanted to attack a high-flying bomber, and it tilted its nose up 10 or 15 degrees, it lost a lot of its thrust. And as a result, it just couldn't catch up with the bomber, no matter what it tried. So the Navy said, oh yeah, I'll tell you what we'll do. And I never saw this in the newspapers. Riley knows about it, I know about it, and some of us who worked at NASA. But the Navy went to the Army and said, let us have a secret demonstration. You put up a bomber, and we'll see if we can't shoot it down. And the Army says, yay, well, that's good. We'll show you how it's going to happen. But what the Navy didn't tell the Army was what they were planning to do was to take a fast-moving F-9F airplane, which had, remember those airplanes, they had fuel tanks on the ends of the wings? Take those fuel tanks off. Take the fuel tanks off. And in its place, put rocket engines, you see? And then in this demonstration, here's what was going to happen. The bomber was going to fly along, and the Navy would come along with their fighter plane and get as close as possible. When they would start losing thrust, the pilot would push a button, turn on the rocket engines, which did not depend on air at all, you see, and whoop, they would catch up with the bomber, and boom, they would blow it apart, or at least theoretically. So they were going to have a great big demonstration to show that this could be done. And everything was getting ready. They took the airplane, they took off the tanks, they put on these engines. The engines happened to be, as I remember, they were made by reaction motors. They were Lark engines, 220 pounds thrust each one. And that was enough at that time to do the job. But there was a lonely little scientist or engineer in the Pentagon. Didn't have much to do. He was reading articles in the paper, as a lot of people do when they don't have much to do. And he saw an article about something that happened in England. The British had developed what they call the Alpha rocket, which worked beautifully. Every time they fired it, boom, it went off, no problem, nothing. So somebody said, well, let's see how it works at high altitudes. So they took an airplane and they flew up to 50,000 feet, and they put a alpha rocket in the belly of the airplane, and then when they got to 50,000, they opened up the thing and let the rocket fall. And by remote control, they pushed a button to ignite the rocket, and the rocket would fly off. Or so they thought. So they dropped the rocket. Ted? Okay, we're waiting for the tape to be changed. There you go.
Okay.
Okay? So they dropped the rocket, it goes down a couple hundred feet, and the guy in a high-flying airplane pushed the button, and there was boom, the rocket blew apart. Well, they said, oh, something's wrong with the rocket. So they took another rocket, they tried it again, they dropped it, pushed the button, boom, blew apart. They did this a few times, and they said, wow, maybe something's wrong with the rocket. So they tried it down on the ground. And when they tried it on the ground, the rocket worked real nicely. Then he said, hey, it's a good rocket, let's take it up. So they take it up, push the button, boom, it would blow apart. But they didn't know why. They had no idea. And this little engineer's reading about this stuff in the trade journal or wherever, and he got a little bit worried. So he went to the Navy. He said, hey, Navy, look what I'm reading over here. What if you take that airplane and you're going to catch the bomber, and right at the moment you're ready to catch the bomber, the pilot pushes the button, and then boom, look, man, no wings, you know, it'll blow the airplane apart. And the Navy said, oh yeah, hey, that might happen, right? Yeah, that might happen. Well, what do we do now? You know, all these brilliant scientists, now they got something, they don't know what to do. So they said, well, who knows something about this? And they came over to our laboratory here in Cleveland, and they said, who knows anything about ignition here? And they looked at Riley, they looked at me and a couple other guys. They said, okay, you work on it. Find out if that's going to happen or not. And they gave us 30 days to find it out. You know, they couldn't find out in a lifetime, and a little dummy like me, I'm supposed to find out in 30 days. But NASA said, hey, we're going to give you the full use of the laboratory. Anything you want is your wish. It was like utopia, you know, like Cinderella. Whatever I wanted, they give it to me. And it was beautiful, except we worked 24 hours a day, 7 days a week. And we had the answer in 30 days. I'll tell you about it in a moment. I felt before that time, this test took place in 1950, or just about that time. And we had started work in 1948 on this. And it had something to do with ignition delay. What exactly, we didn't know. Was it the low temperatures of high space that was causing the problem? Or was it the low pressure? Because down here, where we're sitting now, the molecules of air, how close are they together, Riley? 1/millionth of an inch apart? I ask him all the questions. I don't know the answers. Ted, you know everything. They're very close together. But I do know that when you go up to 70,000 feet, you know how far the molecules are apart? The molecules of air, thanks. The molecules of air at 70,000 feet are 21 miles apart. So there is not too much air up in that area. Good. So back in '48, what we had started to do was to make simulated rockets to find out what causes all of this. And I made a 50-pound thrust rocket. and it had a steel plate on top and a steel plate on the bottom. But the combustion chamber was made out of some material that was transparent. Transparent. My little granddaughter's repeating it after me. I used lucite, which turned out to be a real good thing. And then we were able to inject a fuel and oxidant into that little rocket engine under varying conditions. I wrote a whole thesis. My doctor's degree was based mainly on that thing. And it's right here, you can look at it later. I was going to describe it to you, but I'm getting tired, and maybe you're getting tired too. So I'm going to cut out 90% of the speech. You see, I'm only 10% through, and the 90%, well, I'm going to stop that part anyhow. But we pushed the button, and the stuff came in, and we looked real hard, and, you know, ignition took place real fast. We said, doggone it, how are we going to see that? So it happened too darn fast. So the next thing we did was to get a high-speed camera. And this high-speed camera ran 5,000 pictures in 1 second. That is, no, minute, second. Second, 5,000. Yeah. No, 5,000 frames a second. Yeah, it was 5,000 frames a second. It was so fast, it was mind-boggling. And so I put the camera up there, and I says, okay, Riley, push the button, or whoever was doing it, and I wait there, and I pushed the camera to start it, and I develop it. Too late, everything's all over. So then I said, I'll push it first. And I pushed it first and then ran it. There was nothing, it was blank, because the film whipped through that camera so fast that a 100-foot roll was used up before you could say, boom, like that, it was all finished. So I got real disgusted. I said, I'll never make this. And then we got the idea, well, we'll use automatic timers. And when the ignition goes on, when the rocket goes on, it will automatically start the camera. And that worked like a charm. And I took thousands and thousands of feet of film. We could see the two jets coming in. We could see them hit. Then we could see a turbulence inside of the engine. And then it would turn brown because there was a lot of products of combustion, and they were all dirty and black. But the moment ignition took place, that clear combustion chamber would get clear within 1 or 2 frames, which meant that whatever was happening in a fraction of 1,000th of a second. So that is pretty doggone fast. In fact, we didn't count it as seconds, we were counting it as thousandths or a millisecond. A millisecond is 1,000th of a second. Okay, so then we started trying all sorts of propellants and combinations, and some of them blew up the engine, some did not. We did not know why. So we ran test after test. You try this. You know, if you run enough tests and then you look at all your results, you're bound to get some sort of a correlation. This is what we did. Sometimes we'd press the button, we'd try a new combination, and we'd hear a big bang, and the roof would lift up in the test cell. Of course, we weren't in the same room. Oh, no, not us. We were hiding like cowards behind a great big wall of concrete, which was, how thick was it? 3 or 4, and there was boilerplate on the inside. We didn't even look through windows. We looked through periscopes just in case something would come at us through the window. So we were not very brave. But we found that there was some correlation between low temperature, low pressure, and so on. And when this thing came up with the Army and Navy, they focused in on us and they said, you get together and give us an answer. So we did. We built a huge tank, 1,500 cubic feet. I have a picture of it in here. I don't know if you can show it or not. Maybe you're not interested. The tank was about 15 feet in diameter and about 50 feet long. See if you can hold it up, Albert. Okay, we
Half the size of this one.
yeah, it was pretty big.
Height, width, length.
Yeah, okay, so what we did on one end, we built a great big flange and we put a big bath. And in this bath, we took a rocket engine, this Lark engine that we're going to tie onto the wings, and we submerged it in a bath of alcohol and carbon dioxide and antifreeze and everything else, and we took the temperature down to minus 40 degrees Fahrenheit. The nozzle projected into this huge tank, and then we took a great big vacuum pump and went chunk, 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 and we sucked all the air out of the vacuum pump.
That's the side way. Well, that's okay. You can get a general idea of how big it is.
There's a guy sitting on top of it.
You know, the picture is sideways, and it was sitting on the ground, but here's a fellow doing something on top of the tank.
So we tried this at the same conditions that the Alpha rocket did not succeed in Britain. We went down to minus 40 degrees Fahrenheit, and we pumped out the tank so it was at the same pressure that we would have had at 40,000 feet altitude. And we said, hey, okay, we're all ready. And this was about a week before the end of the 30 days. That's how fast we worked. We worked like dogs. And the first test that we had, all the bigwigs wanted to see it. So, was that Silverstein was there at that time, or was it Dr. Sharp? You don't remember? Anyway, the big shots all came from the administration building, and it was like a national holiday. They surrounded the test area in a great big circle. All these people, you know, and I went into the test area behind the great big wall and everything else, and everything was ready, and we watched the gauges, and when the temperature was down to minus 40 and the pressure was at 40,000 feet, I says, this is it. I pushed the button, and there was a roar that you could hear about 10 miles, and the thing exploded and blew every which way, and you never saw so many ants disappearing in all your life. Boy, those people ran, and they ran every which way. You know, these big shots who are very normally are very sedate, well, they could run pretty darn fast, I found out. We had other tests after that, a lot of tests. They never showed up again. They would call up from the front, how's everything going? To make a long story short, I wrote a report at the end of the 30-day period, and the summary is this. I will guarantee you that if that pilot goes up to 40,000 feet with those Lark engines on his wingtips, and if he pushes that button, he will indeed go somewhere. He'll go to kingdom come, but he's not going to catch that bomber. And that's how it ended. All of a sudden, everything got quiet. No more controversy between the Army and the Navy, but they did come back to us and they said, well, if it doesn't work, can you make it work, you know? Well, we did. We spent the next 6 years on it, but we did make it work. To tell you what was wrong, it was nothing more than using the wrong combinations of the wrong propellants. Well, they weren't wrong. We didn't know any better, but we had to find new combinations. For example, the early ones that we had ignition delays, that is from the time it went in until it ignited, of about 3,000 milliseconds. That's 3 seconds. In other words, the stuff was going in